Hey everyone, I'm GoldenSound, you're watching The Headphone Show by Headphones.com, and in my reviews I often take a look inside various different DACs and amps and call out design aspects that I think are particularly good or concerningly bad, but many of you watching might not know what all of the stuff inside a product like this actually does, and so I thought, let's go through it. Have a look inside a few different DACs, talk through what each part does, why it matters, how they differ across products at different price points as well, and what I look for so that if you're buying a product in future, you can have a look inside too and have a better understanding of what the actual hardware is that you're buying. We've already talked about the inner workings of how both R2R and Delta Sigma DACs actually operate in our DACs 101 video, and I'd recommend going and watching that first if you've not seen it already, but for the other hardware, let's go through a couple examples. And I've started with these two. This is the Eversolo DAC Z8 as an example of a more moderately priced DAC, and this is the Ferrum Wandler as an example of a slightly higher end one. I've picked these two because even though they're at quite different price points, they are actually using the same DAC chip, though as you can see just by glancing at them, the rest of the design is quite different. And then later on we'll look at a higher end and proprietary design DAC, the Hollow May, as an example of how different things can get when a company is doing almost everything in-house. There are four key areas to any DAC. There is the power supply, the digital section, the DAC section itself, and the analog output section. First things first, the power supply. Everything needs electricity, and so you gotta have a power supply. This can either be internal to the unit or external. In the case of the DAC Z8, this entire left-hand board here is the power supply, and as shown by the fact that it takes mains voltage input, the power supply is an internal one. It has one job: take the alternating current mains voltage supply and convert it to a fixed output DC voltage supply. With the Wandler, the power supply is actually external, as shown by the fact that rather than taking straight mains input, it takes a DC input, either via the barrel jack or the 4-terminal connection if you're using Ferrum's own Hypsos power supply. This stuff all on the left here isn't a power supply in and of itself. As said, it's already taking a DC input. This is actually all just filtering and voltage regulation circuitry to further remove any noise and regulate and hold the voltage ultra stable beyond what the power supply was already doing. There's two main types of power supply: switching and linear power supplies, and this is quite a point of contention in the audio world, with many people saying that linear power supplies are just straight up better, even though that's not actually a particularly good rule. If you want to be able to just look at something and know if it is a linear or a switching power supply, the general rule is look for a big transformer. If it's got a big transformer in it, it is probably a linear power supply, and if it doesn't, it is probably a switching power supply. In the audiophile world, you will regularly see people saying that linear power supplies are just better than switching power supplies because switching power supplies are noisier. And whilst that's technically true, in practice, not really. It's true that switching power supplies inherently generate a huge amount of high frequency noise. They are switching between fully off and fully on at very high frequencies, whereas linear power supplies don't need any of those switching components, so they're not generating it in the first place. But in practice, switching power supplies now, any modern decent quality one, they don't switch at 30, 40, 50 kilohertz like they often used to. Many of them switch at hundreds of kilohertz, far higher frequencies that are far easier to just completely filter out. Roden Schwartz has a really good video explaining how switching power supplies work, so if you do want to know more, I would recommend going and watching that. And linear power supplies have some unique challenges that people don't recognize or talk about all that often, such as the fact that those big transformers are a source of noise and interference. As you put the incoming mains AC through them, they generate a 50 or 60 Hz electromagnetic field, which can be picked up and interfere with other areas of the product. This is why if you look at measurements for various different DACs and amps, especially with linear power supplies that are internal to the device and therefore the transformer is physically closer to other areas of the product, devices with linear power supplies, you'll often see some noise around 50 or 60 Hz and multiples of it, whereas switching power supplies, often it's just not there. And actually, just to illustrate the point that switching power supplies can indeed not only be just as good, but in some cases quite a bit better than many linear power supplies, I'll link in the description to a post on Audiophile Style where someone measured a bunch of external audiophile power supplies, and the lowest noise and ripple option by a fair margin was the iFi iPower, which is a reasonably affordable switching power supply. Once it has its primary DC supply, the DAC then needs to convert that DC voltage to various different DC voltages, because different areas and components on the board will need different supply voltages. If we look at the bottom left-hand corner of the DAC Z8, we can actually see a number of engineering probe points here, so you can just put an oscilloscope probe on them. This is mostly used for servicing and the R&D purposes, but it shows us the different voltages that are actually coming out of the power supply section. It's not just one. On a lower cost product like the Z8, this is generally going to be done with fewer components. On the Wandler, which costs a fair bit more, this entire left-hand section is for filtering out any lingering noise that might be remaining on the incoming DC supply, separating into various different DC voltages, and regulating, holding those voltages ultra stable even if the load presented by the different components that they're supplying changes. In higher end products, you would generally want to see more filtering and regulation stuff going on, because I want more of my money to be going to the actual product, not the manufacturer's pocket, and that is probably one of the main differences that we can see between these two products here. Something that is quite important to look for when you are shopping for and comparing DACs, because, well, it affects whether you're going to end up with the right product for you or not, is, well, if you look here on the Z8, you might need to look real closely. Can you see it? That is a 365-day return policy from headphones.com, which means that if you buy a product and you're not super keen on it, you can just send it back up to a full year later. Supporting headphones.com also supports everything we do on this channel, so if you like educational content and everything else we do here, consider headphones.com for your next audio purchase, because it's what makes all of this possible. Anyway, back to the video. Now we move on to the digital sections. A DAC needs to be able to take various different digital inputs, USB, AES, SPDIF, sometimes I2S or HDMI ARC as well, and you'll usually find the components for this pretty close to those digital inputs. On the DAC Z8, this Exmos chip is what's acting as our USB receiver. Exmos is probably the most common brand of USB receiver that you'll see. They're pretty ubiquitous, whereas with SPDIF, AES receiver chips, you'll see a bit more of a variety. Companies like AKM, ESS, Cirrus, Texas Instruments all have their own ones, and in the DAC Z8 it's actually using a Cirrus one. The purpose of these is generally to receive the SPDIF data, for instance, and convert and hand it off to the DAC in a format it can actually understand. Most DAC chips can't just take SPDIF directly, they need one of these chips to translate what's coming in. Typically, that receiver chip will then hand off the signal in a format it can understand either to the DAC chip or in many cases an intermediate control component. On the DAC Z8, that would be this component right here, and it'll do various things besides just the digital audio handling. It allows you to control the DAC, change oversampling settings, change digital volume control, it might drive the display, and often it'll also control various other aspects of the actual hardware. So in the Z8, for instance, there's relays, switches next to the outputs and the headphone output, and you need a way to control which output is being used, so that's probably being handled by this too. You might also see various other components and hardware in the digital section of a typical DAC. For instance, on the Z8, there's also this green daughter board. There's a bit of a hint as the fact that it's connected right next to this antenna for the Bluetooth connection, and it is indeed a Bluetooth receiver. Some other DACs, particularly higher end ones, might have a network streamer as well. But if you're not sure what a particular thing does when you're looking inside a product, just Google the part number. For instance, if I didn't know what this particular chip was, I can just Google Cirrus CS8422, and it quickly tells me this is a high-performance 24-bit stereo asynchronous sample rate converter and SPDIF receiver chip. It is right next to the SPDIF inputs, so that makes sense. That is our SPDIF receiver. On the Wandler and many other high-end products, things can work a little bit differently. Rather than having separate USB and SPDIF receivers, something else for driving the display, something else for doing DSP, it's quite common to see things combined into either one processor, FPGA, or module, and that's what's happening here. Our USB, SPDIF, I2S inputs, everything is all going into this SERDSA module. And as we can see from the fact that there are no other processors or FPGAs on the board, this is also what's doing all of our compute, DSP, and driving the display, as well as facilitating the other features that this device has. It is quite common on higher end products in particular to see more resources put towards compute power to enable things like, well, higher performance DSP, so oversampling, for instance. I think Chord is maybe the best example of this. Even in their portable products, they put pretty expensive, powerful FPGAs to do much more advanced digital processing, the oversampling, than what the DAC itself is actually able to do internally. Once we've done all of our input receiver stuff, any DSP that we want to do, converted the output to a format that the DAC itself can actually understand, then we need to hand all of that off from the digital section to the actual DAC. The DAC Z8 has a small heatsink on top of the DAC chip, so you can't see the label, but both the Wandler and the Z8 are actually using the exact same DAC chip. This is the part that actually takes the ones and zeros, the digital information, and outputs the analog waveform that we want. For more information on how a DAC itself actually works, go and watch our DACs 101 video. Digital audio is sampled data. Most music is 44.1 kHz, but regardless of whether you're running a NOS DAC, which doesn't do any digital processing at all, so it's just running at 44.1 kHz, or in the case of both of these, an oversampling DAC that converts to and runs at a much higher rate, you need something to tell the DAC, okay, now do the next sample, and now the next one, and now the next one. because if you convert the right data at the wrong time, this creates distortion known as jitter. So we need a timing control signal, and this is provided by these components here called clocks. Crystal oscillators, typically just referred to as clocks, provide a fixed frequency output signal that the DAC uses to know when to do the next operation. There is a bit of a difference between the two we can see here, because again, if you're getting a higher end DAC, there is more money available to be and hopefully is being spent on better components, and clocks are no different. Higher end DACs will usually have higher end clocks that should in theory provide better jitter performance. They should have less variation in what the frequency they're outputting is. But I can't stress enough, don't just look at how fancy the expensive clock inside a device looks, look at the actual measured behavior of the product as a whole. The clock itself is only part of the story, and there are plenty of products with really expensive fancy clocks that don't have great jitter performance because the implementation is bad. So what makes a good clock implementation? Well, primarily two things: the voltage supply to the clock itself and the signal path from the clock to the DAC. Clocks rely on a stable DC input voltage to remain stable in their output. And actually, if we look at both of these products a little bit closer, we can see that as well as all the filtering and regulation from the power supply itself, there's then some additional voltage regulation right next to the clock to ensure that the clock's DC voltage supply is as clean and stable as possible, ensuring that the clock performs as optimally as possible. And the second aspect is that on both of these products, the clock itself is in very close physical proximity to the DAC. The clock signal does not have very far to go to get to the destination, meaning there's far less chance of any signal degradation due to interference, impedance mismatches, and other problems, and as a result, both of these DACs have excellent jitter performance. The Wondler's is slightly better, maybe because it's using a slightly nicer clock, I'm not sure, but Z8 also shows that implementing the clocking well with a cheaper clock is far more important than a bigger, fancier clock alone, since on something like a Denafrips Terminator Plus, the jitter performance is not as good despite having a big, fancy, expensive, oven-controlled clock. So I think that's quite a good example of why it's certainly still nice to see a higher end clock in a device, particularly if you're paying more for it. It's still much more important that things are implemented properly. And again, check the measurements, don't just look at how expensive that particular component is. Actually, fun fact, this signal path challenge is a big part of the reason why external clocks almost always make DACs perform worse, not better, but that's a topic for another video. The DAC itself converts the digital information to an analog output, and then we have this area. This is the current to voltage, or IV stage. A lot of DACs don't actually regulate output voltage, they regulate output current, and so you need some circuitry to convert this to a voltage output signal. This can be done in a variety of ways, and it is going to depend on the particular DAC that's being used in the product. I wouldn't make a direct comparison between the IV stage for an AKM chip and the IV stage for an ESS chip, because they do have different requirements. But actually, as you can see here, even though these two products are both using the same DAC chip, the IV stages do look quite different. Some of this could just be the fact that, again, on a higher end product, there's more budget to put towards a more robust or higher performing solution, and some of it is also just down to the fact that different manufacturers have different ideas on the best way to do this. But once we've converted the analog output from the DAC from a current signal to a voltage signal, now we move on from the IV stage to the analog stage, or the output buffer stage. And this does two things. Firstly, it sometimes provides some amplification for the signal, taking it up to whatever the output voltage you want at the output of the product is, so typically around 4 volts for XLR and 2 volts for RCA. And it also, as the name output buffer implies, provides a buffer. It ensures that no matter what the conditions downstream in your chain are, even if you're running either an amp where the load is changing depending on what it's doing, or a difficult thing like a passive preamplifier, for example, or just really long cables, nothing is going to weaken or distort the output of the DAC itself. It gives the DAC the easiest time possible, and then it provides the actual driving signal to the downstream components. The output stage in the Wondler has a fair bit extra going on compared to the Z8, and from a quick glance at the circuit itself, it's not necessarily clear why. But an easy answer for a lot of this stuff is, again, if you're not sure what a particular component is doing, just Google it. Have a look at the part number and see what it says when you look at the datasheet. These chips, for instance, are analog volume control chips, so we know that this part of the Wondler's output stage is a preamp circuit for facilitating analog volume control. One of the other types of component you'll see very often are relays, which typically look like larger white boxes. Relays are switches used for connecting and disconnecting various components, areas of a circuit, or outputs, and it's not uncommon, including in both of these products, to see them right at the output of DACs. This is usually so that the outputs can be completely disconnected whilst the DAC is turning on, or sometimes just changing state, just to ensure that no clicks, pops, or other unwanted output feeds through to the amplifier running, because that can be either annoying or potentially dangerous if it's high enough in level, and then whenever the DAC is ready and stable, it'll connect both the outputs again. Sometimes it's also, like in the case of the Z8, so that you can switch between the headphone output and the DAC output without the DAC itself actually having to have separate DAC output channels routing to different areas of a product. But relays will also be found in areas of a circuit that don't always need to be in the signal path so that they can be disconnected when needed. For instance, in the Wandler, you can see that these two here actually connect or disconnect the preamp circuit so that if you're not using the preamp circuit, you can just bypass that whole section entirely. It's also just good and sometimes fun to be curious about a product and see what you can work out about it from what you can see inside, and doing things like just tracing the path of a signal along the PCB if it's visible. So on the Wandler, it's got some analog inputs, and if I was thinking, are these going through an analog to digital converter, or is it actually remaining analog the whole way through? Well, let's see if we can work it out. These are the analog inputs of the Wandler here, and we can trace these to these two analog buffer stages. We can confirm just to be sure that none of these are analog to digital converters by just, again, Googling the part numbers if we wanted. They are input buffers. And then from the output of those input buffers, we can see that the signal path comes down to this relay. And given as that is right next to the analog preamp section, we can be pretty confident that that means it's switching to either being disconnected or going into the analog preamp section. From there, we can further look along the trace to see the output of the preamp section goes to these relays, into the actual final output buffer, and then through to the analog outputs. We can also just double check, have a look around, see are there any components here which are analog to digital converters? Nope, there aren't any. So the combination of those two things, we can be pretty certain that, yeah, this acts as a fully analog preamp if you're using the analog inputs. Whereas if there was a product where it was going through an analog to digital converter, you would probably be able to trace that signal path to an ADC chip of some sort. So even if it's not on the product page, you can often work this stuff out by just looking inside and having a look where things are going. But from there, that's kind of it. We had our power supply, our digital inputs and digital processing sections, feeding off to the DAC itself, the DAC's output being converted from current to voltage, going into the final analog output buffer stage, and then that just connects straight to the final XLR or RCA outputs. We have our final analog output signal. Hopefully that gave you a bit better an understanding of how to identify the different areas inside a DAC, what the different components are actually doing, how they might be done differently in products at different price points, and a better understanding of where your money is going if you are buying a higher end product in particular. But on that note, let's have a look now at something quite a bit more expensive to see how much things can change when you look at something completely proprietary. This is the HoloMay R2R DAC. It's quite a good example of a DAC where almost everything has been designed in-house, as well as just generally having a lot more put into the hardware. Starting with the power supply, it is a little bit more substantial. It is a linear power supply, as you can tell from the large transformers, and then there is a ton of filtering and voltage regulation circuitry all over the place as well. In fact, this power supply alone is quite a bit bigger than either of the other DACs we looked at in their entirety. This is also a dual mono power supply, where it's got completely separate power supplies for the left and right channels of the DAC, as well as the power supply channels being separated by this physical barrier in the middle here, which is pretty neat to see. And the power supply on this DAC is a separate unit, because as we talked about earlier, linear power supplies, particularly the transformers in them, are a source of interference. So if you are using linear power supplies, it can be beneficial to have those transformers and the power supply itself be physically distant from the rest of the DAC if possible. Obviously that incurs more cost because you've got to have another chassis and all the extra stuff to connect them, but it's nice to do if you can. Then moving on to the main unit of the May, this does look quite different to what we saw in the DAC Z8 and the Wandler, but all the same key areas are here, so let's go have a look at them. Firstly, there's the digital inputs, same as what we saw on, say, the DAC Z8. They look a little bit different. The USB has a separate daughter board in the May, and it's not using an XMOS chip. In this case, it's actually using an in-house self-developed solution, because the May supports much higher input sample rates than many other DACs do. This will go up to 1.536 megahertz PCM, or DSD1024 if you want to do that. And one thing that I always check for, particularly on higher end DACs with the USB input particularly, is galvanic isolation. These two components here, as well as the physical gap in the PCB, mean that there isn't actually, technically, an electrical connection between the USB host side of the board and the DAC side of the board. In fact, if you look at the back, there is a gap between the chassis and the input USB connector to prevent it touching and connecting the USB ground to the DAC's ground. With the combination of those optical isolation chips and having everything else literally not even touching, it means that you can have full galvanic isolation, full separation between the USB input side and prevent any kind of noise that might have been generated by your PC or other noisy source potentially from getting through to and affecting the performance of the DAC. That's something that I personally like to see in DACs just because it means you can just hook your DAC straight up to your PC and not worry about whether your GPU or something is going to send noise shooting through. There are a lot of DACs which can be susceptible to source noise, and full galvanic isolation like this means you don't need to worry about it. You don't need to go buy DDCs or fancy streamers. You can just connect it via USB and not worry. For the other inputs, it's relatively similar to what we saw on the DAC Z8. There is an SPDIF receiver chip right here. There's an AKM one in this case, rather than Cirrus. And the I2S input on this is a discrete, self-developed design. But once again, all of this gets handed off to an intermediate control component. So probably one of these two FPGAs here. Now, there are two, which is a little unusual, or actually not that unusual. One of these will be handling all the same housekeeping features, so turning the DAC off and on, letting you change settings, controlling the muting relays near the outputs and stuff like that. The other one, which has a little hint to it as it's right next to the clocks, is handling a bunch of advanced clocking management features. So some DACs will use this for things like synchronizing with an external clock, or in this case, it's used to run a PLL with the inputs from SPDIF and I2S. This means that it can attenuate jitter that might be present on the input signals and replace it with its own clock signals to get the best performance out of the DACs themselves. You can also see that there is a ton of filtering and voltage regulation circuitry, not just down here in the power supply, but next to just about every single critical component. It's hard to say how much of a difference that's actually going to make, but it's just one of those things where if you're spending a ton of money on a high-end product, you want more of your money to be spent on the product and not just going into the manufacturer's pocket. So still nice to see. But then again, much like the Z8 or the Wonder, once we've had our inputs received, had our clocking sorted, converted to a format that the DACs can actually understand, we need to hand off to the DACs themselves. On the May, this is a dual mono DAC, so rather than just having one DAC which handles both left and right output channels, it has completely separate DACs for each channel, and in this case, physically separated quite far from each other, the idea here being that it reduces something called crosstalk. Crosstalk is when the output from the right channel leaks into the left channel or vice versa, and physically separating your left and right output channels means there is less chance that stuff from here is going to be picked up here, and vice versa. This is also an area though that whilst it is nice to see this kind of design aspect, check the measurements, because there are tons of products which are technically dual mono that still don't have great crosstalk, especially if the DACs are still quite close to each other, and there are products like the Z8 and the Wonder, in fact, which despite just running a single DAC and a not dual mono, the crosstalk is down near minus 140 dB, so it's a cool design aspect, but you should check the measurements because at the end of the day, it doesn't matter if it looks cool if it's not doing the thing that it's supposed to do. Being a proprietary design, this is not using off-the-shelf chips. They're using Hollow's own self-designed R2R ladder modules in this case, though there are other manufacturers that make DACs their own self-developed designs that are Delta Sigma ones. Chord has the pulse array design, DCS has the ring DAC design, and there are many other manufacturers, including some that don't even use them all the time. TNA, the DAC 200, uses a Burr Brown chip for just regular PCM input, but if you feed it DSD, they have their own self-developed DAC, which it switches to for that. I unfortunately can't lift off these shields to actually show you the May DAC modules, though here are some images of them. I don't have the right Allen key to get these shields off, so I'll have to live with that. But I do have the Cyan 2 module, which is pretty similar. The May's modules are basically much beefed up versions of this, so we can take a closer peek. The bottom half of the module is an R2R ladder for converting PCM audio. Again, if you want to learn how these work, go and watch our DACs 101 video. And the top half is a 1-bit DSD converter for converting DSD audio. There's also some pretty cool stuff if you look really closely, like how the traces to each of the elements are shaped so that regardless of their position, all of the traces have identical length. Which when you're working with incredibly high frequency stuff like high rate DSD, the travel time of signals can start to have an effect, so stuff like that, which ensures signals to each element arrive at the same time, is kind of nice to see. Then right after the DAC modules, just like we saw in the DAC Z8 and the Wonder, we have the current to voltage or IV stage, and then immediately after that we have the analog output stage. There's also a bunch more filtering and power regulation stuff going on for those stages here too. So this DAC might look a fair bit more intimidating at first glance, but hopefully after watching this video you know that it's all the same building blocks. Power supply, digital inputs, some kind of handling feature, the DAC, current to voltage, and the output stage. that's it. That's how basically all DACs are built, and hopefully after watching this video, you've got a better picture of how to look inside any DAC and know a bit more about what's going on, see which products are doing certain areas better or more comprehensively than others, and a better idea of where your money is going for the products that you're spending money on. There is one other thing that I did want to talk about in this video, which is that FPGA DACs don't exist. But we are already running a little bit long on time for this one, so I think instead of putting it in this video, I'm going to put that on my forum thread at the headphones.com forum. There'll be a link to that in the description. And if you've got any other questions that you wanted to ask me about anything talked about in this video, DACs, amps, music, gear, anything else at all, come and say hey on the headphones.com forum or the headphones.com Discord server, where I and other wiggly air enthusiasts will endeavor to help. Till next time, I'm GoldenSound. You're watching The Headphone Show by headphones.com. See you next time.